if one could discuss. There are a lot of things which one can discuss in the context of performance optimization, so I have to actually restrict it a bit. And in order to, I will start with, say, a more general, say, short chapter, so to give you a little bit of a background. And then I will look into 3 areas, and it's really more, say, touching it, even though it will take us, say, maybe say about an hour, but still I will not get, say, too deep into that, because all the topics which I'm touching here, you could have, say, a lecture of 1 hour itself, right? So we have to do a bit of a compromise. But I try to focus on things which, where actually there is a bit of a connection also to the numerical exercise, which we have seen also for the hands-on. So in this way, I hope that we can, say, convince you that everything is indeed, say, connected. Now, give me, say, some of the, say, the broader background. I thought it's useful before we start to look into different optimization strategies to also, say, make you aware that, say, a lot of the research in this area is also, I mean, well, part of it is, of course, driven by, say, looking at very specific applications. But some part also have been driven by, say, the observation that even though we might have, say, very different types of computations, that there's also similarities, right? So that, just to take one example, I mean, I'm originally coming, say, from high energy physics. I mean, what, say, people doing in theoretical high energy physics when they try to simulate the theory for strong interactions with an approach which is called lattice QCD, actually, if we look at it in terms of the computational patterns, they are not too far away from what people from the computational fluid dynamics are doing when they use the lattice-Boltzmann method, right? And that really has to do because there are, say, certain computational patterns which we find back in different applications. And this is an observation which has at some point been also written down in a technical report. I think it was actually from Berkeley, which is called the Landscape of Parallel Computing Research, a View from Berkeley. But basically the term which is, say, more widely known is essentially it's about the Berkeley dwarfs, right? So one dwarf is essentially an algorithmic method that captures a pattern of computation and communication, and which you will find in multiple, say, computations. And the goal here is say, to identify then, say, commonalities then between, say, different number of applications so that you can exploit common knowledge, right? So if you have the same type of computational patterns in a theoretical high energy physics problem as well as a computational fluid dynamics problem, I mean, then you can actually start to think, okay, I mean, are there optimization techniques which applies to both domains, and can we, say, develop, say, best practices and how to implement that? And the answer is yes, we can do that, right? Now, by now there have been, say, 13 different graphs which have been identified, and don't worry, I won't take you to all of them. I will just focus on 2 of them, which I say the most well-known, and will, at least one of them will also have a direct, say, connection to the problem which we will look at in the hands-on. But for, say, the HPC part, it is really, say, these ones which are, say, the most important one. So I will get you to the dense linear algebra, and will also get you to the structured grids. In some sense, I mean, there is also a bit of a connection between, say, sparse linear algebra and structured grids. What is also, say, quite important is, for instance, n-body methods. So in astronomy and also in biophysics, when you think about, for instance, MD simulations that are, say, n-body simulations, right? Because you have to basically, you spend a lot of time in just computing, say, forces between, say, the particles. So let's look at the first of the 2 ones where I will just focus on here, and that is, say, the structured grids. So there are applications which, say, perform, say, periodic updates of something which is living on a regular multidimensional grid. So think, for instance, about if you want to solve, say, for instance, the Maxwell equations for electrodynamics, right? So then we're living in a 3-dimensional world, and we want to say, we have differential equations, which we can then discretize, and essentially we have then on all the grid points, we do have then, say, we can associate a value with the electric field, and then because the magnetic fields do have, say, some of the fields have directions that we can associate two links. The same would also occur, and that's actually where we also will look for the numerical example. I mean, for instance, on heat equations, so the Poisson equation, where we look for the simpler case of say, the 2 dimensions. But again, the story is the same. You have something which you can, say, discretize on a regular grid, and in order to solve the numerical problem, you do regular updates of the grid, right? So the application areas are, so let me first point out, I mean, what is basically, what are the key features here is, well, it is mainly in terms of the memory access. We have, say, strided memory access, so we have, say, a regular access to the memory. I mean, it could be, say, that you go from one element to the next element, so you have stride 1, but there might also be jumps in there, but at least it's a very regular access pattern, which, for instance, from the architectural perspective, has an impact also on, think about, for instance, memory prefetchers, right? I mean, it's, you can start to make predictions about what are the next locations of memory which you access. But you can also start to think more carefully, and that's also one thing which we will touch on here in this lecture, on is there, say, data locality, where data locality means that there's an opportunity for reusing data. Right? We will look at it more carefully later. Now, there are, say, quite a number of application areas where this is. I mean, I mentioned already, say, heat transfer, lattice quantum chromodynamics, but also the CFD, specifically when used the lattice Boltzmann. Right? For other areas with finite element of, so it gets a bit more complex, but say lattice Boltzmann is a simple one in some sense when you look at it from the computational perspective. Now let's look at a specific example, and that's also the example for the hands-on. That is the Poisson equation. And we just for to have it not completely trivial but also not too complex, let's do it in 2 dimensions, and so it can be formulated in a continuum as an differential equations, where you have then here, say, from the field V, I mean, you have then a second order derivative in x direction and y direction, and then you have here on the right hand side you have then, say, the kind of field which defines, say, the boundary conditions. Now, we don't want to go too deep into the physics behind it, but just say focus on the numerics in order to arrive on what are the computational patterns there. So let's say look at what is, say, with this formulation in the continuum. We can now, say, discretize it, and we would now have, say, we have here a central point, and then we have here the neighbors. And now let's assume that the first index is, say, connected to the x direction. So that's why we have here, say, the neighbor in the minus direction and the neighbor in the plus direction. And we divide it here by the discretization constant h, right? And because it's second order, we get here an h squared. Now, if you use this discretization, I mean, you can, say, now formulate this equation also as a matrix equation. You could just write here, instead of having, say, this differential equation, write here a matrix T and multiply it here, this V with it, and have then moving this h square in the denominator here on the right hand side, and we have it here F, where F is now, say, something which is discretized over our regular 2-dimensional grid. Right? And now we can look at, say, this matrix, and what you will find is that it's, say, a very regular but sparse matrix, because you have here this on the diagonal. I mean, you have 4 because we get the 2 times the central value from both the x direction and from the y direction. That gives the 4, and then we have here -1, which say corresponds to the neighbors. Right? So we have essentially here a sparse matrix where, if we look in one row, we have almost everything is 0 except for the points where we have on the diagonal, and one where we have, say, a neighbor, right? And in 2 dimensions we have at most 4 neighbors. So there's basically 5 elements in one row or in one column is non-zero. Yeah? So obviously it would probably not be a good idea to write it as an explicit matrix, right? Because it would be a bit of an, stupid idea to use all the memory for just storing zeros. And that's also not what one does, but if one looks at the graphical representation, then we can actually learn, say, two things. Is if you update, say, one point here, then we need to know all the neighbors. Right? So essentially, it is, say, relatively straightforward to collect all this information without really having to think about it as a matrix times vector operation, even so we could mathematically formally write to it. And so if we implement it, and that's also what you will find in an example program, you will never see that one would, say, really implement it as a matrix vector implementation. One way of expression is it's basically, say, a matrix V implementation. That is a kind of slang which you find back in the literature. And to basically on the fly say compute what are my neighbors in order to find this update. And now because you have this kind of patterns, which is basically you have a stencil here, that's why these structured grid applications are often also called stencil applications, right? It's just a kind of different terminologies, but essentially you end up with dealing with structured grids. Now, from this graphical representation, there is another thing which one can learn from that. And that is, if we, say, first update this point here. So let's assume that we just move here through this lattice and this way and update all the points. If we update this point, then we need this point as an input and this point as an input. If we later update this one, we need these 2 points again, right? And this is what is called temporal locality, right? It is basically when we access one data element in one point of time, there is a high probability of that the same data is needed in the near future. Right? And that is something which one can try to exploit in the architectures, but it's of course also something for the optimization that one may be trying to think, okay, could I actually do things such that I can exploit this data locality, right? And that has also something to do in the way of how I organize this update, or how I run through the memory, so that I can do things in a way that it becomes rather impossible to exploit this data locality, and I can do it in a way where I can exploit this data locality. Now, let's look into a second computational dwarf. That's the dense linear algebra. And that is, essentially, the kind of other extreme. Before we could think about, say, the structured grids you can mathematically represent as a sparse matrix multiplication. Here, we're now talking about a dense matrix times, in this case, this example, vector multiplication, right? So dense doesn't mean that there might be also some elements which are zero, but most of the elements are non-zero, right? So you have no choice but in your computer to really, say, store the full matrix. And again, we have, say, as a typical access pattern is that we have, say, a unit stride or fixed stride regular sequential access. So there's nothing, say, very irregular. So think about this case which is shown here. We have basically a matrix A times X, and so in order to compute one element of Y over here, we have to, say, compute the sum, and so we are running, say, regularly here through this over these indices, right? So we first will access here the first element of X, then the next X element, and so on. Here is X, so we would have 1, 2, 3, 4. Now, if you would have, say, this very simple operation, I mean, typically, say, one way of optimization is to look for a library which has an optimized implementation for that, and say for the most important dense linear algebra kernels, they are available in BLAS, which stands for Basic Linear Algebra Subprogram, which have been well, I think in the 90s this was developed, and there's still a reference implementation around, which is the NetLib BLAS, but certainly not recommended to use it because that is completely unoptimized. But since then there have been a lot of research in trying to see, okay, what actually is a good way of having an optimal implementation of that. And what is probably the most popular one in the open source space is OpenBLAS, but also Bliss has, say, very interesting features. But they have, to some extent, they have a similar kind of background. But also a lot of vendors started to develop their own versions of these BLAS library because that's a way of how to promote also, say, the hardware products. And so for Intel you have MKL, IBM has ESSL, and also ARM, because I mean they have their core designs, so they can start to produce, even so they don't build the hardware, but they can, say, produce then also software which is optimized for their designs, and that's also what they're doing. They have the ARM performance libraries. Now, of course, these ones, they are typically, well, all three of them are closed source, so you have not an access, and you might even have to pay a license fee in order to be able to use it. So that might also be a business model from these companies to actually get access to that. Now, just for your additional background, I mean, there's not, I mean, there are different types of these kind of linear algebra operations. They have been classified in terms of BLAS 1, 2, 3, so where BLAS 1 is, say, the scalar operations and vector or vector-vector operations. Then the example here where you have a matrix vector operation is BLAS 2, and BLAS 3 would be matrix multiplication. Okay, so with that, I mean, just for you to know, to remember, there are, say, these computational patterns which are described by these dwarfs and which you find in different applications. And we just went through two of them that are the structured grids and the dense linear algebra. Now let's look into, and that's where I will come back also to say these two dwarfs. Let's look into three optimization techniques. And the first is when it comes to, say, memory access. And now, before we get into, say, the optimization approaches, strategies which you can employ there, let's look a bit more carefully into this data locality, which I already was introduced in the context of the dwarfs. And I mean, the interest behind that is just based on an empirical observation. And the empirical observation is that programs tend to reuse data, and that's also true for instructions that have been used recently. And so that's the reason why you find in a lot of compute architectures, not necessarily all of them, but at least a number of compute architectures, they heavily bet on having so-called caches in place. And they are there for exploiting memory localities. And so this is an observation which you then can use to improve performance or optimize the use of more or less expensive memory. So the idea is if we could have say, have this data locality and maybe you could use, say, very expensive but very fast memory in order to, say, keep part of this data, which we then can reuse, then this is something which pays off. Now, there's two types of data locality which are distinguished here and which are also important because they also have different consequences for, say, the computer architectures. One is called the temporal locality. Temporal locality means that if you use a data item, there is a high probability that you reuse this data item in the near future. So there's the time separation. And the spatial locality means that if you read something from one address, that there is a high probability that you also read from a nearby memory location. So think about, for instance, if you just do a memory copy, so you copy one array on the other one, then you access element 0 of an array, and then you access the element 1 of this array, and then the element 2, right? So in other words, once you start to access the first element of this array, you continue by accessing elements which are in the near vicinity of this first one, right? So this is a clear case of the spatial locality. We can also look at it, and this is just, say, a very artificial example of code, just to show of what does it mean with, say, these two different localities. So let's assume we have a two-dimensional array, A and B, and that we have somehow B is already initialized with some value, and now we want to update A in this set of nested loops. Right? And now in C, the convention is that the rightmost index is the fastest running index. Right? So that means that if we say, when it comes to access of A, which in this case is actually in write access, because here in this inner loop we have J, which is running from 1 to n minus 1, we are basically accessing next addresses in memory. So here we have a clear case of having here a spatial locality, right? Because if we access A, I, and J, then we will basically, in the next iteration of this inner loop, we will access I and J plus 1. Now we don't have, and that is important to realize, we don't have a spatial locality in this case, here in the case of B, because now in the case of B, it is now the leftmost index, which is, say, incremented. And that's where we're making a bigger jumps. Essentially, we're jumping here by n elements when we increment now here this J. However, we still have a temporal locality here, right? Because when we access J0 in one iteration, and then J is incremented by 1, and the next iteration we access J minus 1, it's the same element. So in each next iteration, we reuse one element of B, and that gives us, say, the temporal locality. So has it become clear what the meaning of spatial and temporal locality is? Okay. Yeah. So for the architecture, say, the simple consequence which have been taken for that is, say, to introduce caches. And the caches has, in particular, say, a role when it comes to temporal locality. So it is, say, basically doing a bet. If I load something into the processor, then it gets loaded into the cache, and that it stays there until the cache, until I somehow need it for other purposes. But if I'm lucky, and also if I optimize my application, then I will have, say, the temporal locality kicks in early enough, and I can use the data while it is still in the cache. Now, caches are organized such that you're not loading a single element of A or B, or in this case we have doubles. That means we're not loading 8 bytes into our cache. Caches are organized in cache lines, and the cache lines are typically much larger than 8 byte. So what you will typically see is, say, a cache line size of 64 bytes. So that's quite common in a lot of architectures. It's also, for instance, the case for the Compaq 920. But there are also cases where it is larger. So Power has at least, I think even including level 1, I'm not sure, at least for level 2 it has 128 byte. And the other extreme is the A64FX, which even has 256 byte. Right? So you can have very large cache lines. And that is really making a bet on the spatial locality. Right? So if I load one element of, say, for instance, such an array, then I will load a full cache line. So I'm not only loading 8 bytes, but I might load, for instance, 64 bytes. But if I have a stride 1 access, I will basically, in the next loop iterations, I will access the 7 other elements of this cache line. So I will make a full use of this cache line without having to load more data from the memory. And the benefit for that is that it's, say, much faster if I load larger chunks of data instead of, I mean, it would be a complete overkill if I would start to load single bytes, right? Because I would not get any good performance, but that would probably now get a bit too much into computer architectures. Okay. Now let's try whether you can, with this background, can already discover of what is the problem of these two of these implementations. So basically, I did something which is, say, relatively similar to what we introduced earlier today. So, but instead of having, say, an array, a one-dimensional array of A, where we add just a constant, we have now a two-dimensional array A, and then we have, after adding the constant, we store it in B. And now we have here two implementations, and the only difference here is that between these two implementations, I swapped the loops. So in the left case, the outer loop is over J, and here the outer loop is over I. But here the inner loop body is exactly the same in both cases. So functionally, both implementations do exactly the same thing. Right? So I hope that is easy to see. But now the question is, and of course the code is written in C, so the convention is rightmost index is fastest running index. Which one of the codes will be the faster one? Fine? Yes. Does everybody agree on that? Yeah. I mean, the reason for that is with this write implementation here, we have now stride one access, right? Because now J is here the innermost loop index, so in each iteration we increment by one. While here we have, say, the leftmost index which is incrementing, so we're basically doing big jumps, right? So basically what we do here in this case, in each iteration, we are, say, opening a new cache line for accessing the array A, right? Well, here we are essentially following, say, one cache line, and you can also see it. So I tried here to provide you, say, with a picture, and so in memory, and that is now for C, where the rightmost index is the fastest running index. For C, say the element 0, 0 will be, say, the first element in memory. Then we get 0, 1, and so on. And now if we assume these are doubles, and we have a cache line size of 64 bytes, it would be 8 elements of A or B would be here on one cache line. And now we have here the second cache line which is starting. Right? So if we, say, do the memory access that we have now here, that we increment the rightmost index, we nicely sit on the same cache line and reuse this cache line. And at some point we will start here now to activate the next cache line and so on. If you would, say, follow here, what is happening here on the right side is we would basically go here from element 0, 0, then the next one would be 1, 0, which is all the way over here, right? So we would do a very big jump in, say, at the end, the address space, right? So we clearly would have then new cache lines being opened. And now if we assume that n is very large, then it might be even worse. I mean, we're not only, say, loading a cache line and only using one element of this cache line, so only 1/8 of the cache line. I mean, of course, we still would have temporal locality because at some point we will use this one, right? But this might happen so late that it's already evicted from the cache, so we have to reload it, right? So there's no chance of actually reusing this data. So takeaway here is it is really important to think about how do I access, say, the memory such that it becomes optimal for exploiting, say, the cache hierarchy which I have in my processor architecture. So if I have this kind of strided access, I mean, things are a bit simple. There are also cases, and I won't go too deeply because it's also not part of the exercise here, but I just wanted to point it out. There might also be cases, and that would be more in the case, for instance, of an n-body code, where I would have, for instance, I have, say, a list of particles, and now I basically look at, say, some property which is stored in the variable a, and now I want to have this value from all the neighbors, for instance, the value of the charges or the forces, and now I go basically through a list of neighbors here, and I sum everything and put it here into B. So the problem which I have now is that now I have a neighbor list, and this neighbor list can be, say, be differently. So NNB is the number of neighbors. So as soon as I have basically a particle I have a certain number of neighbors, and now I run here in this inner loop over all the neighbors. And then the exact number of the neighbor is now encoded here in this list. This is of integers in this list NB. Now, the challenge that I now have is that now memory latencies become an issue, because I can only start to load A once I have loaded here the neighbor list, right? So I have first to know what is the number of what is the neighbor before I can access this neighbor. And so I have one memory, one load instruction, which then only can be, and then a follow upload instruction, which only can be scheduled once the previous load started. So now it's not depending on, say, the bandwidth, because it's not a question of how much data can I load per time unit, but how quickly can I load a small piece of data. And the other thing is, well, obviously, I mean, it depends a bit on the neighbor list, but obviously I have no guarantee that this is now, say, a simple access pattern, right? I mean, it could be completely random of how I get now through the memory. And a third challenge is, how the hell do I actually vectorize this? Now, unfortunately, it's possible, but it does have a penalty. And the reason why it's possible is that now modern processor architecture start to support what are called gather instructions, gather load instructions more specifically. What that means is that when I have one instruction to load, but I essentially give this load instructions not only one address, but multiple addresses. And in this way, I can still vectorize it. But again, it comes with a penalty, and that is still, say, something which is, I would say, an active area of research. Now, unfortunately, there are not simple recipes for how to optimize it. I mean, the most important, but of course that doesn't always help. The most important one is try to avoid having any kind of lists. So, if you have a problem where, like we had, for instance, I mean, of course, you could also use neighbor lists in the central application, which we had looked before, right? It's perfectly valid, and when I started to do programming, I mean, it was a good way of doing it, because at that time, I mean, this is now talking about the 90s, I mean, you still had a lot of memory bandwidth available, and it was quite common that you used also for central application, you use neighbor lists, right? But nowadays, I mean, the available memory bandwidth is a limiting factor, so try to avoid using neighbor lists and spend rather a few instructions to recompute your neighbors. Yeah.
You mean we would unroll this loop so that we can match it to the cache line size and have these operations also include on the contained cache line?
No, I mean, this is, when it comes to vectorization, I will, in the last section, I will explain a bit more. I did already introduce, say, this SIMD instructions. So it's essentially about being able to map things onto vector registers. Right? Okay. I mean, they could be of the same size as a cache line. So think, for instance, about AVX 512. 512-bit is 64 byte. So here, say, the register can hold a full cache line, but the SIMD registers might be also significantly smaller than a cache line.
Okay.
And typically, you would also end up, for instance, when you have a gather instruction, which is referring to completely different locations in your memory. You might actually hit and activate a number of cache lines and read, say, one data element from this cache line and then merge it into one SIMD register. Right? But then you have it in one SIMD register, and then you can start to do all your computational operations on this one SIMD register. right? So that's where it's still beneficial to do that. But the getter instructions can be quite expensive. But that would get now a bit too much detail. But
what I was thinking about was when we already know the cache byte size, we can unroll our loop such that we have all this operation that will be taking place on the same cache line as the instructions, instead of having the loop goes through it and goes to the registry, registry all the time.
Yeah, but I mean, you would not have to do a loop unrolling for optimizer for a cache line, right? I mean, this is really the way of how you access the memory. So you could have a loop where in each loop iteration you have say you access one element of this cache line, right? And because the core sees the memory only through the cache. So I mean, when you pretend in the core to do a load from memory, it arrives at the cache controller, and the cache controller says, oh yeah, but you are trying to access an element of the memory where I have a copy in the cache. Right? So even if you have then a simple 8-byte load in a loop, and in each loop iteration you do a single load, then it would be, say, a load from the same cache line. Now, of course, in practice, it might happen that you are not, say, efficiently using, say, the access then to the cache, because the ports to the cache are often larger than 64 bits or 8 bytes, right? So that's where it becomes beneficial to use actually then SIMD load instructions. But it doesn't have to be then a scatter loads, right? I mean, if you have contiguous memory, then you would gain already. And that's, for instance, the reason why in this example which we showed this, have seen this morning, that say things improved because the compiler was doing this vectorization, right? Even though it was still, say, memory bandwidth limited. Now, the other, say, strategy which can also help here is when you have, say, the opportunity to sort your data, right? So that, I mean, there might be still irregularities in your neighbor list, but then try to organize these neighbor lists in a way that that you have, say, an as regular access to the memory, and that could, for instance, also include trying to reflect, okay, trying to stick into your cache line before accessing other parts of the memory. Okay, with that, coming to the next area of how to optimize things, and here I want now to take an example of a more, say, dense linear problem. It's exactly, say, this BLAST2 operation where we have matrix vector operations. And if you would do it, say, in this very naive way, and you say, okay, I mean, I just implement it as I have it in my, say, mathematical expression, where I have this sum, what would be happen there? Now, the important thing is for this operation to realize is that there is a temporal locality, and the temporal locality is not in A. For A, we only have a spatial locality, right? Because we access one element and the next, and so on, right? So that's where we have a spatial locality. But we have a temporal locality because whenever we increment I, we always go through the full vector x. We always load the full area of x. Right? So that's where we have a temporal locality. Whenever we increment I, we go through all elements of x. Now, assume that we have n being very, very large. Then the problem is that if we do things in the way as it is shown here in this picture, so we basically take one full row of A in order to multiply it then with x, then when we then start with processing the next row and get to all elements of x, that x is not in the cache anymore, or at least the first elements of x are not in the cache anymore, right? So this is true if you have when you have really very large n. So one way to say, one technique which is quite common and can be applied in many cases is, which helps to avoid this, is called cache blocking. And I think it's more easy to understand it in a pictorial way. If I would move here, through my array A, not in the way as it is shown here, so that I do, say, column by column, but I organize it in the way that I, say, form this kind of blocks, and I go only through one part of the row, so for instance in the first half of the row, then go into the next row, and so on. The benefit which I would have is, here I would basically, if that is A00, 0, I would have to multiply A00 with X0. Then I have A01 multiplied by X1. And here I would then access X2. Now I switch the rows, and here I start again to access X0. And here X1. But because here I do start doing this already much earlier than I would do it here, because if n is very large, it might take me very long until I'm back here when I'm using again X0. I have now a much higher chance of that X0 is still in the cache. Right? So, and this is a trick which is called cache blocking. Now obviously, I mean, things looks now a bit weird, in particular with this example where I have now an odd number of points here. And obviously I start to also read now in a bit non-linear way through the memory, right? So that's where I have to basically do some bargaining, because I have now here one element of A, the next element of A, and yet another element of A. And then I do a big jump because I'm moving all the way here, right? Because in memory, the next one would be over here. Right? So, yeah.
So we plan to do more for it with the matrix. It would make sense to transpose it so we have the original case we can just keep operating on the same line with the same cache.
If you apply, say, more multiplication with the matrix A, yes, and then you would have to reorganize it, because then you start to get temporal locality in A, right? So here I assume that I just have a single multiplication of A times X, and so I basically read each element of A once, and I don't reuse it again. If that assumption doesn't hold, then of course I have to rethink about that. Right? So I here focus just on how can I exploit the temporal locality which I have with X. But of course I potentially pay the price of that I do not fully exploit, particularly in this, say, cartoon case where, say, I have now, say, the blocks are very small, that I do not fully exploit the spatial locality in the case of A. So of course, then the code starts to look a bit ugly. And that's where you can start to play all kinds of games of how to make it then more nicer. And if you want to see of how then really complex code look like, then you have to talk to Stepan, who did this optimizations for, say, the dense matrix multiplications. So there's a lot of tricks which you can play to really max the performance. That becomes non-trivial, but the idea is essentially the same behind that. So essentially what we now start to have is we now have to say run here also. We have now more loops, because now we have also the loops over the different blocks, right? So we basically double the number of loops which we need to do our computation. Now there is not, because we also want to have some hands-on later, there is not sufficient time to actually go into all details, but I would just like to highlight that one can analyze this case with not too much effort as a pen and paper exercise, using this information exchange approach which I was introducing this morning. And essentially you can, say, compute now the, so this is the information exchange which refers to the number of floating point operations which have to be performed. And then if I compute that, then I have for each x, I have to perform n multiplications and n minus 1 additions. So that's why I have n plus n minus 1 times n flops. So it scales quadratically with the size of the matrix. But if I look of how much load and store I do have from the memory, I have to store n elements that as the result of y. At the end, I have to access each element of the matrix A. That gives me an n squared. But it's now, in case of x, if I do the blocking, If I would have no blocking, then I would have to reload each element of x, which gives me 1n, n times, because I have to do it for each element of y. And I would have another n squared here. If I do the blocking, then I get here, instead of having n times n, I get n times n over b. Right? And then it depends on the block size of how much the amount of data reduces which I have to move from the memory. Now, of course, I cannot make b arbitrarily large, because that would assume that I have an infinitely large cache. But if I have a very large cache, then I can, say, go for a large block size. And with that, I can actually then also show that I have, say, if I go look into this extreme, I can actually show that I have I can change the arithmetic intensity. I can increase the arithmetic intensity from 1/8 to 1/4. So just as an illustration that one can use the kind of techniques which were introduced in this morning. And now it doesn't mean that this, say, trivially translates into performance improvements, but this is now with, say, very simple code as it was shown 2 slides ago, done on a notebook processor. And what you can see here is, say, the execution time as a function of the block size. And what you can see here is that if I would have no cache blocking, that I have a large execution time, which drops if I quite quickly if I do just a little bit of a blocking, and then it increases again and becomes a bit saturated at some point. So I don't gain too much by increasing the block size further. Now, the claim here is that I can get, I mean, overall the speed up is quite large, right? I mean, I'm talking here about more than a factor 2 speed up, which I can obtain with a not too complicated trick. And the claim is, of course, that I get this speed up just because I'm making more efficient use of the caches. And I can actually then also use, say, what we learned about PARPI this morning. For instance, look into the level 1 data cache miscounters. And I can see here that I indeed find here that, say, the cache counter is, say, decreasing. And then again, I find a bit of an increase and that's, say, a bit of a side effect. I mean, the cache behavior is not that easy as it might have seemed, and then I still have a bit of an increase, but at least I can see here that if I would have a blocking size of 8, which corresponds to, say, the best performance in when I look at the execution time, it also, say, corresponds to having, say, a very small number of cache misses. So in this way, I can, say, claim that by, say, optimizing for, say, doing this cache blocking, that I, say, gain from that. Now, I didn't investigate exactly on why I have a bit more complex structure. I'm speculating here a bit, is that I start to also get some conflicts with the memory prefetcher, and probably get some conflicts with the memory prefetcher, so I get less efficient in terms of how to access the memory. And at the end, recall that we are talking about increasing the arithmetic intensity from 1/8 to 1/4. At the end, with the improvement, still the arithmetic intensity is small. So we are still having a memory bandwidth limited problem. And so if we, say, change the memory access pattern, we might also change it in a way that, say, the performance on how to read the memory is becoming less optimal, which is probably the consequence of that is what we're seeing here is that we have, say, if we make the block size too large, that performance drops. Okay. Any questions concerning cache blocking? Then let's look in, say, the third strategy for doing, say, optimizations. And this is, say, a slide which I have shown you exactly already, say, in this morning. It's just a reminder about the SIMD instructions. So again, recall SIMD instructions means that I operate on small vectors. So in this case, it would be a vector of 4 elements. That could be, for instance, 4 a double, so we would have then 4 times 64 bit. So one vector would be then 256 bit, and it requires only one instruction to add then 2 of these small vectors. And that is something which you could, for instance, do with ARM AVX or AVX2, or if you have an SVE with 256-bit, also that could be done in one instruction. Now, the question is how to use, say, these SIMD instructions. Now, in the sake of time, I mean, I only introduce here one way of actually making use of these SIMD instructions, and that is actually leave the work to the compiler. Compilers have become, say, surprisingly smart. And I can really tell, we could really prove it. I mean, there had been recently, we published also a paper on that where we tested the compilers on how clever they are in terms of vectorization, and they are surprisingly clever, meanwhile. What does auto-vectorization mean? It refers to the ability of the compiler to convert operations on scalars to operations on vectors. So it's about the compiler to detect that it's possible, even so you might just have a loop, as we have seen it in all the examples before, where you basically sequentially access, say, different elements, to detect, oh, but you are basically accessing, say, sequentially into some elements, and now I can just map it onto, say, a vector or SIMD instruction. Now, the advantage, obviously, is if I leave it to the compiler is that I have code which is just a standard C code. Alternatives is to use, for instance, inline assembler, or to use something which is called intrinsics, but then I do something which is instruction set architecture specific. Here I do everything at the level of the high level language, so my code remains completely portable. The other benefit is that, of course, the programmer is relieved from doing, say, complex code transformations. But of course, it has its limitations, right? Because I have now maybe only indirect control on how the code is being generated, and the compiler may fail to identify vectorization opportunities. So even so, the compiler has become very clever. It doesn't detect all cases, and because it's, say, another proof of the non-existence of the free lunch, you may have to provide things in a way that the compiler can actually understand that you can vectorize it, right? And so there are things we actually want to look a little bit into and still stick it on a very simple example, and that is the DAXP example, which I had already introduced this morning. So DAXP means D stands for double, and then we have A as a scalar times X, where X is a vector, plus Y, where Y is then a second vector, and Y is overwritten. So here I write it with, say, calling the scalar alpha times X plus Y, and then Y is overwritten. So that's how you can implement it in C. So now I just took this code and put it into the current GCC, which is installed on the Kunpeng cluster. That is, I think it was the GCC 12. But with these simple ones, I mean, there has not been so much changes of the compilers recently. There's only two things which I did here is, so with 03, I told GCC to enable, say, essentially all optimizations, which in this case includes also the vectorizer, right? And we have seen it in the example this morning that the vectorizer kicks in. The only thing which I did here is that I added this option, and this is only telling the compiler, please provide me with some information about what you're actually doing, right? So just if you add, I mean, it doesn't change the behavior of the compiler except for that it prints additional information, and I put some of the information I put here. And in this case, it actually did say, okay, vectorized one loop in function, and it refers here to line 6. And so this line 3 is basically, that is the function, and line 6 is referring here. So it says, okay, here I identified an opportunity for vectorization and did the vectorization. Now, what is actually not so easy to grab from this, I mean, I admit that these kind of messages is sometimes also a bit cryptic. What is not so easy to grab is that it also gives here, say, a warning about possible aliasing. Now, what does it mean, aliasing? There is, I mean, if for those few people which started to learn, say, programming with Fortran, I'm always happy to admit that sometimes there is really great benefits of Fortran over C. C allows you to provides you with a lot of freedom. And one of the freedoms which you have in C is that as the function as it's called here, x and y may refer to the same memory region. So the compiler doesn't actually know whether it's possibly having some issues with overwriting something, right? And that is called aliasing, right? In Fortran, if, say, x and y would refer to the same memory region, I mean, the compiler is not able to detect it, but it would be non-standard compliant. So you as a programmer would have violated the standard, and so it's you as a programmer to blame that what you're doing, right? But here in C, it's perfectly fine to do that. So the compiler cannot assume that x and y are referring to different memory regions. And this has a consequence in, say, the code which is being generated. So, I mean, you can just, I didn't copy the assembly here, but I basically wrote it here in a way that you have here the -s. You can easily look in the assembler, and then you will see that there's quite a lot of code which is being generated. And that's only in order to protect for these kind of situations where basically x and y are referring to the same memory region. Now, the C standard has over time, took them 20 years, but at some point they learned it's a good idea to also allow the programmer to tell the function, no, you can assume that there's two different memory regions, right? And that happened when this additional clause restrict was introduced. So this is yet another, say, simple, say, recipe for optimization. So if you, say, call a function with pointers, and you really know that these pointers are referring to disjoint memory region, don't forget to put the restrict clause in there. And as you can see here now, I mean, if you look at the output, say the output became much shorter because the vectorizer did see, okay, there's now no risk of aliasing anymore. And actually the code became much simpler, and it's now fits on the slide. In the previous case, the code would not have fit on the slide because it now splits it up in multiple loops. But now we essentially have a kind of a loop construct. I mean, we have seen this already, say, before. So we have here, this is the loop body. And so we have here the loads of x and y. We have diffuse, multiply, add. And we have here the stored, and we have here the increment of the loop variable. And we can see here, so this is now compiled for the Kunpeng. It's not the case of SVE as we have seen in this morning. So it's for the Kunpeng, and it's now vectorized for Neon, 128-bit. So we have now here an increment by 16 byte. So it's of course not so easy to understand that these are indeed vector instructions, but this becomes only clear when you look at the registers. And also, as already pointed out, now the loop variable, which is stored in the register x2, is incremented by 16. And this way we can really see that this loop has been properly vectorized for the Kunpeng processor. Okay, that's all for the optimization. And going back yet a bit more in history, so that was one of the first computers from Leibniz, mechanical computers. That was certainly not particularly fast, but if some of you ever happen to be in Böblingen at the IBM Development Lab, they have a very nice exhibition, and I think they also, it's from time to time open for the public, where they have, say, mechanical, say, computers at the time. I don't remember how the company was called before it became IBM. That existed until the 20s, 30s, so then it became already IBM in say, the location yesterday. And it's really impressive of how fast also mechanical computers can be. So it's not just the electronic computers. Okay, with that, thank you very much, and I'm open for if there's any remaining questions. Yeah.
So if you talk about the performance gains you can get from using data caching, but there's also performance costs, and we know that we won't be using the caching won't work for some. We are just writing the matrix and we are just generating it, and we'll be using it a way later date when our cache has been replaced many times. So I think there would be a point to give the compiler instructions to bypass the caching right directly to memory.
Well, this is very architecture specific, so this is not something which you can generalize. So by default, I mean, everything runs through the cache, and then it depends a bit on the architecture, whereas you have support for, say, optimizing this, and for instance, also has support for what is in some cases called non-temporal loads. But how the processor architecture reacts to that, that of course is very product specific. Right, so that's why I didn't go through that here. I mean, it's not only say about necessarily bypassing the caches. I mean, there's also say effects where I haven't talked about here. Is there's I mean, I mentioned it here because we're not talking about ARM architectures. ARM has in its architecture an optimization which is called say the write buffer mode. And that is related to trying to do following optimization. So if I have, say, no, that's not a good case. That's not a good case. Do I have still this other example? Oh yes, that will be an example. So. Here I'm updating, say, this two-dimensional array B. It's not important that it's two-dimensional, but I'm updating B. And if let's get for this example, in this case here, so J is the innermost loop. And so I'm writing to one element of B and then to the next element and so on. So maybe if you do the next one. So if that is B, we write here, we write here, we write here, and so on. So what we're eventually doing is we're overwriting a full cache line. The problem, however, is what the hardware sees is I do a store to the first element, then I do a store to the second element. And it would require a crystal ball for the processor core to understand, oh yeah, that will continue until I overwrite the last element. So that has a very odd implication. And the implication of that is that because the compiler, the hardware cannot predict that I will overwrite the full cache line, is it has no choice but to load B and then update basically the different elements of the cache line and then eventually to write. So naively I would think, okay, I have to only load A and I don't have to load B. Well, in terms of instructions, it's true. But what the hardware actually would do is, or very likely doing, if it has no optimization, it would actually load both A and B. But for no good reason, because B is completely overwritten. Right? Now, in ARM, there is in the architecture is foreseen, say, an optimization technique, and to basically speculate that the full cache line is overwritten. And so in this way, you can bypass, avoid, say, this additional reads. So there are this kind of say, optimizations also at the hardware level, and this is now a specific ARM type of optimization. There are some similar things also in the Intel architecture with the write buffers, but so there are ways of how to avoid, say, the unwanted cache behavior. But if you have, say, completely random memory access, then, I mean, you have to, say, to worry about that you might indeed for each element of an array which you access, not just load one element, but you always load a different cache line. And that could, in case where I say have doubles, mean that my maximum performance actually drops by a factor of 8. Right? Because instead of loading 8 bytes, I load 64 bytes. So. Mm-hmm.
In ARM, it would speculate the cache line or make sure in that case, isn't it's like compared checking out on the cache line every time, and then if it's same, and it's not same, then it's loading. Is that true?
Well, I don't see another way of actually how it could be implemented. I mean, I must admit, I haven't seen any vendor actually documenting of how they have implemented it.
I was thinking that if that's the case, then isn't it making again slower? Because checking will take time.
Yes, but this is the same if you also think about techniques like, say, doing, say, speculative branch execution. And at the end, just from, say, practical observation, it's something which works, right? Of course, it's not guaranteed to work. I mean, it only works if most of the time you are speculating, you're not misspeculating, and if the penalty for mispeculation is sufficiently small.
I can understand it makes sense if you have a vector operation and then you know that if it's a vector operation and you are loading every time a full batch of cache, then I only need to know if it's same or different.
Yeah.
In that case, you have to make some performance, but for the general calculation, in that case, or in a non-vector calculation, that may not be same, and then you are like working slow in this case.
Well, the only thing I can say that, I mean, again, it's not say a fundamental law of nature which guarantees you to have this spatial locality. It is just practical experience that you gain from assuming that you have sufficient spatial locality. Also take into account that if you would start to do very fine-grained memory access, that you would have so much overhead that essentially you wouldn't gain.
Yeah, that makes it more specialized with that kind of application. With vector mainly.
Yeah, I mean, again, it's just, say, empirical, right? I mean, why do you go for 64-byte cache lines? Well, you could argue that say, I mean, it helps you to distribute things, to parallelize it over more, say, memory controllers. But why not go for 128 bytes, right? And so it's just, say, a bit of an, say, general experience for, say, big chip makers that this is a reasonable compromise.
In that case, we need to go more specific to the code side, so that even for the general case, we try to map that with the vector architecture.
Yes, that's a good point. I mean, it's really a bit the question of what is the impact on the code. And there is indeed, say, one of the challenges, I mean, both when it comes to cache optimization as well as when it comes to optimization for SIMD vectors, is you will often find that there is a very subtle dependence on the data layout. And my advice would be is to try to formulate applications in a way where you have a sufficient, and what sufficient means, that would be a longer discussion which you can only do for the specific case. Try to have a sufficient flexibility on reorganizing your data layout. And you might have heard about, say, for instance, terms like structure of arrays and arrays of structures. Right? And that is a typical example of that. On some architectures, it might be better to have structure of arrays. So, for instance, on GPU-like architecture, that typically works better. Or an array of structures where you might be able to exploit, say, more data locality if you have the caches available. Now, the question is, can I formulate my application that I can switch between different data layouts without, say, generating a lot of code or having completely different code, right? And that's where people have started to work on. I mean, you might end up with having, say, if you do it in C++, of getting, say, very complex template expressions. That can pay off or not, but I can give you examples where this definitely did pay off, but I would not recommend it as being that the best possible recipes. But in general, I think this is one of the key challenges for modern application design of how do I do it that I still have, say, the sufficient flexibility in my data layout.
But even in that case, you can choose the programming language, but the compiler is doing the same work. And in that case, as you mentioned, compiler doesn't allow much extensive ability to us to change something while they are compiled. And in that case, we should be aware of the architecture.
Mm-hmm.
So either we had a very efficient compiler, or our program should be like really good for the architecture.
Yeah, I tried to explain a bit in an example. I mean, I'm not a fan of, say, assuming, say, the super smart compiler, because the compilers get, I mean, they are quite amazing in what they can do. But if you talk, for instance, about some people which try to do with, say, directive-based programming, like OpenMP or OpenACC, where you, say, aim for the compiler doing a lot of very complex things. If the compiler fails, then you are in a super odd situation, because then it becomes very, very difficult to understand what the compiler did wrong. And it already becomes very difficult, I mean, already with auto-vectorization. I mean, I have seen codes where it was very hard for me to understand of how does it actually relate with the original C code or the original Volcano code. But I think it is important to understand, at least to some extent, on what the compiler is doing and how can I formulate things also in C or Fortran such that they help the compiler. Right. I mean, as one example, I mean, this for this Poisson equation, right? I mean, we could have implemented this with just using neighbor lists, right? But then the compiler has no clue about the memory access because everything is hidden in a neighbor list, which is generated somewhere else, right? But if I explicitly say do a recomputation of neighbors, then the compiler gets some understanding of what I'm doing. Then the compiler gets a chance of maybe doing a vectorization, which it otherwise couldn't do. So for me, this is a very good example where you can actually see that you can make it, doing the same thing, you can make it easier or more difficult to the compiler to actually optimize it. And this is the kind of awareness which we should have. We should not think the compiler can do everything. We should be aware that there are some limitations, and that's why I also introduced, for instance, how can I make the compiler give me information about where did vectorization succeed and where it didn't succeed. Now, it might be sometimes cryptic what I get back, but at least I get back information where it succeeded, and then kind of look at the code. Okay, maybe I did something which makes it indeed where it's known that it's difficult to vectorize, and maybe you can think about how can I reformulate the code such I can actually vectorize.
Yeah, and in that case, we also can use different tools like different modeling and other things, so we can evaluate.
Yeah, I mean, when you get to this level of detail, probably the roofline model doesn't help you sufficiently anymore. But I mean, the thing about the roofline model as basically a first approximation on getting some understanding of how much performance should I get, right? So that I essentially know, okay, I mean, that's a simple case is, I mean, and it's not so unrealistic. I mean, there is, for instance, I was mentioning, say, the top 500 list with the high performance Lindmark benchmark. There is, yet another sister, except for the green 500, which is essentially a benchmark which is measuring depends very much on the memory bandwidth. And if you look at the floating point performance of this benchmark, it's very low. And I remember, when I was still in Jülich, these discussions where at that time it was Norbert Attig, okay, no, we can't report, performance figures where we only have 3 or 4% of our peak performance, right? Yes, that may be right. You don't have to look at the super deployment operations. If you know the roofline model, you know you have to look at the memory bandwidth. And if you can report we are using 100% of the memory bandwidth, perfect. Unfortunately, that never happened, so that, say, for this benchmark, still people report, say, the performance in terms of throughput of flops and not in terms of memory bandwidth would be more appropriate. So that's where a roofline can help you, but it's just a more first guidance, but then things can also come quickly more difficult. So maybe for having a further code break, should we maybe very briefly look into the example code?
You mean start with Python?
Yeah.